Good afternoon, everybody. So today, right before we get started, I want to cover a little bit of what I'm going to be going over and what I will not be going over. This might help you shape some of your questions for the end. So we're going to be talking today about VPNFilter, a little bit about the campaign as a whole, as well as specifically the Modbus specific capabilities of this malware sample. But what we won't be talking about at all is attribution, any of the partners Talos worked with, or the victims as a whole. So without further ado, let's get on with it. So VPNFilter was disclosed in May of 2018. We have proof that this has been going on since roughly 2016, and at the height of the infection, there were roughly 500,000 devices that were infected. Most of these devices being perimeter devices. So we're talking small office, home office, routers, NAS devices. And what's really impressive about this malware is how cross-platform it really became. So not only are we looking at Linux devices that are running BusyBox, we start getting into a highly customized proprietary operating system of Router OS that most of MikroTik's devices are running. Beyond operating systems, we have cross architectures. We're looking at common RISC architectures such as MIPS and ARM, as well as common CISC architectures in x86, as well as additionally, we have uncommon RISC and CISC architectures. One of the uncommon RISC architectures is Lexra, which is what we're going to be focusing on. The uncommon CISC architecture is actually Tile, which seems to be a very rare, if not proprietary, architecture that was designed by MikroTik for their routers. When we were doing this research, there wasn't even a IDA Pro disassembler for Tile to work with. As we go on to what this malware actually targeted, the answer is pretty much everything. Every single one of these manufacturers had at least one device that was targeted by VPNFilter. Specifically, we've highlighted MikroTik and QNAP. The reason for this is because these were the most commonly infected devices that we saw. QNAP, it's likely because these devices all run a very similar operating system across all of their network storage devices. It makes it fairly simple to target all of them, meaning you just have to recompile for a different architecture. What was really surprising, though, was MikroTik. While we were doing our research, we found different samples specifically compiled for over 30 different devices. These were all different architectures and different actual devices. So this ranged from like an outdoor access point all the way to their high-end routers. And so that was something that we noted as interesting and was a focus of other research. So VPNFilter as a whole really was three main stages. Stage one was the persistent loader. Stage two moved on to the actual primary platform. That was where you'd have your operational ability. And then stage three was kind of extensibility, different modules that you wanted to load in if you needed something specific. So this is the general operation of how VPNFilter worked. So once stage one was brought onto the device through some sort of exploitation, it would try to go out to PhotoBucket with a list of accounts and pull photos off of these accounts. It would look for EXIF data from these photos and then pull out a stage two server IP address to go pull down stage two. If that didn't work, it resolved toknowall.com, downloaded a picture, and did the same exact thing. And then as a final backup, it opened up a listener on all possible ports using a raw socket and listened for a specific SYN packet, and then used that IP address to pull down stage two. Once stage two was pulled down, it would try and communicate with command and control and either execute those commands or download additional plugins so that it could have additional features. These plugins really ranged significantly in terms of what their capabilities were. Today we're going to be talking about the packet sniffer module, the first one that you can see here. It would sniff all traffic, log Modbus traffic when it occurred, and then also capture HTTP credentials. Additional modules include SSLer, which would man in the middle all traffic on port 80. It could exfiltrate information as well as inject JavaScript that would be executed on the endpoint. You would have a Tor module, which you could extend C2 communication to the Tor network, as well as a kill-destroy module. So overall, as the value of VPNFilter as a malware campaign is the huge amount of global intelligence and cyber operation infrastructure that you obtain through these 500,000 edge router devices. You can mask attribution by manipulating data flow through all of them, or you can collect data on any of the networks that you have these edge points compromised. You can do active and passive attacks, as well as destructive attacks. As I said earlier, the kill or brick module would overwrite the MBR, the master boot record, with all zeros, and all of your edge network devices would be unbootable. Additionally, you can use this as a jumping off point for exploiting internal networks. Really, it's any other reason that you'd want a botnet, you want VPNFilter. And now we're going to actually move into the specifics of the Modbus module itself. So the packet sniffer module is responsible for HTTP sniffing as well as Modbus sniffing, and the target was specifically the TP-Link R600 VPN. This is a small 5-port Soho router. As you can see with the Shodan scan, there was roughly 500 that were with remote management enabled. And what was really unique was this was the only device that was targeted with this Modbus capability. We had, I believe, roughly 100 other samples, and this did not show up in any other target at all. So a little bit about the device. It runs a Realtek system on chip that utilizes the Lexra MIPS architecture. So unlike MIPS, Lexra doesn't have these 4 instructions. They're useful for reading and writing unaligned words to memory in an architecture that utilizes a aligned memory context. So part of the story behind why they don't have these instructions is because they were patented. Lexra believed that they could get around the patent by just not using them and building a compiler that optimized around that. We had a few challenges with working with Lexra. As we got this sample before we knew what it was targeting, it identifies as MIPS. All the file magic points to MIPS, and when it runs in a emulator, it works fine. Once you try and write proof of concepts or other tools, they won't work on the actual device because they don't have those instructions. So the sample itself, it was first uploaded to VirusTotal in 2016. It's a Linux elf, stripped, and statically compiled. If you don't know what this means, basically it doesn't rely on any external libraries. You don't have any function names, so you have to reverse string copy and string compare and anything else in libc or any of the other common libraries. This makes reversing tedious and can take a long time. A lot of the tools that are designed for identifying these types of library calls are written around x86. You're seeing some more in ARM now, but something like Lexra, which is using a very outdated compiler, you can identify function entry points and exit points easily. So in a basic flow graph, this is what the sample does. It's going to check every packet. It's going to see if the packet's over 150 bytes, if it's IPv4, TCP, and then it will start checks for Modbus and HTTP. So it's important to note here that you want to, when you're building something like this, you need to make sure that you bail out early and often. This sample was utilizing a raw socket, which means that it saw every single packet that came across any interface on the device. So if you don't bail out early, then you are going to significantly degrade the routing capability of your router, which isn't great for stealth. So the sample takes 2 arguments. It actually will parse 3 arguments, never actually uses the 3rd, but if you don't give it 2 arguments, then it won't run. These arguments are a directory for logging and a IP address that's actually used for targeting this application, which we'll talk about a little more, is pretty interesting. The main packet parsing loop isn't incredibly exciting. As I said earlier, it's a raw socket that just listens on every interface and looks for any packet that's greater than 150 bytes. Typically, this would be so that you can filter out a lot of the noise on the network and you don't need to trigger on absolutely everything. So after every packet is intercepted, it checks for, as I said earlier, the number of bytes, if it's IPv4 using the ether type of the packet, and is the packet TCP. It's not very easy to read. The first basic block basically is going over IPv4. Second basic block is going over if it's TCP. Third being if it's actually 502, and this is where we start to get into the Modbus section itself, as well as the fourth block is parsing the IP address. So hopefully you guys can read that at least a little bit. This is, to try and make it a little easier, I avoided assembly. This is actually Binary Ninja's intermediate language. So once we meet all the previous checks of packet size, we actually want to make sure that the destination port is, in fact, 502 for Modbus. Additionally, with that, we check if the destination IP address is equal to the second argument. If all those conditions are met, then the Modbus connection is logged. So originally, when we started this research, it was concerning that this was going to be something that was snooped on or possibly rewritten. But as we reverse the sample, it's actually interesting to find that they just log the time that this happens. And if you look at how much information is actually required by the attacker, they aren't gleaning that much information. And you can tell that it was highly targeted. In this case, you are providing the IP address that it needs to target. You are providing the port that it needs to be targeting. So the only information that you're gleaning here would be from what source IP and what source port. These logs are generated with timestamps, Unix timestamps, and placed in the logging directory that you provided. And this is likely exfiltrated using a different tool or module. And once you find a packet, it just restarts the whole process. If it's a Modbus packet, it's just logged. And if not, then we move on to some other checks. So this is what a Modbus log actually looks like. As I said, it's not very exciting. You're looking at a timestamp, the fact that it tells you it's Modbus, and a incoming IP import to a destination IP that you provided and a destination port that's hard-coded. So some of the open questions that we have here for this sample specifically is, why was this a target? Why was this one specific device a target? Are there ICS environments that are utilizing this specific router? Is that common? Or was it a research project or an abandoned project that the malware authors designed? Or the other possibility is that they had inside information, and this was the exact model that they needed in order to get what they wanted done. So moving on from that, the module actually provides HTTP authentication sniffing as well, and this happens utilizing the same, very similar logic. So we have all the same checks for the actual packet itself. And then we move on to some new checks, including The source port has to be greater than 1024. The source port can't be 108080 or 8088. And the length of TCP data has to be greater than 20 bytes. So this is just the general flow of this sample, this part of the sample. So these are some of the string checks. Once it checks if the TCP data is greater than 20 bytes, it starts to make sure that these strings don't occur in the data. If you look at some of these strings, you're filtering out JavaScript, you're filtering out anything that includes HTML, you're filtering out some failed login attempts or forms that you might come across. And the reason for this is likely because what they're trying to do is target HMIs on a device that has Modbus open. They're looking for something that uses HTTP to run these HMIs, and you don't want to catch any of the data that includes HTTP responses or HTML pages being loaded. Instead, you just want to get authentication packets. So each of these packets have to contain either authorization basic or username password combination. The reason for this is if you're using authorization basic or one of these combinations, you're likely using clear text credentials or something that's easily decoded. You can't have both just because that would kind of be an oddity, and I would assume they're trying to use this to filter out false positives. If the HTTP check fails, the loop restarts and you just go back to the next packet. And if every one of these checks does pass, what we do is we actually log the entire packet. So you're logging the HTTP request most likely. That includes all of your credentials. So it's fairly obvious that this part of the sample is for simple credential harvesting. Again, like I said, it's probably targeting a device that it knows is running Modbus, and it's hoping that there's an HMI that's associated with that Modbus connection. The destination IP needs to be provided in both of these parts of this module. So it's not sniffing your entire network. It's not sniffing every possible connection. It's looking for very specific connections. This would mean that an operator most likely already has intelligence into what's on your network and what there possibly is on each different endpoint. And at this point, they're really just looking for who's talking to your Modbus endpoints, as well as is there any easy credential sniffing that they can acquire. So there's some very interesting things about this specific module. One of them being that this sample is specifically for the R600 VPN router. It was not found anywhere else in any of the 100 samples that we acquired. The destination IP is required. The packets are sent to a specific destination IP that are checked for. The information about the Modbus connections is not logged. Instead, it's just a timestamp and the fact that it occurred. And on top of that, you have full credential logging for any plain text credentials. It's also important to realize that this sample cannot rewrite traffic without a very significant code rewrite. One of the major concerns was that this was going to be modifying Modbus traffic on the fly, and that's just not the case in this current state. So overall, this was a long-term project for most of Talos. There was a lot of other very talented researchers that worked on this, and a lot of their information is also included in this, so I'd like to give everyone a shout out. On top of that, as long as everything went according to plan, there should be a new blog post on the Talos Intelligence blog that actually details a remote code execution on this device that was not previously disclosed. Are there any questions?
I remember seeing it seemed like early on that the word Modbus was largely ignored in VPNFilter. It did kind of catch my eye. I speculated, and I wonder your take on this. Is this perhaps a first example of, for lack of a better term, OT malware escaping into the IT world? Maybe the concept is, well, let's just own all the things. And not only this being the first, that we might see this, we're usually worried about IT getting into OT, but now we're seeing very sophisticated, well-financed attacks on the OT side, and that might escape into the IT world and affect them.
Yeah, I think we are going to start seeing people branch out. I don't know if it's safe to say that this was OT malware that escaped into the IT world, just because of how targeted this specific module was. It's very obvious that it was well-financed and extensible, and this is probably something that we might not have seen all of the possible modules. So it's possible that there were other things such as DMP3 or ENIP or something like that in terms of other protocols that they were trying to sniff. And I think really you can kind of take that as a major takeaway, is that this is the future of extensive malware campaigns, is something that's easily extendable. So if you have a new target or you find information about your network that you are going after, then you can easily build something that will be highly effective in that environment.
Yeah. I mean, it also seems, again, just like the concept of, well, let's just own everything because we can, even if we just need one thing in the universe. And if there are any other.
Thanks. Any other questions? Yes, sir.
Vulnerabilities and the level of quality of stock firmware in SOHO devices is well known and lamented. But there's also now a trend towards third-party firmware such as OpenWRT or OpenVPN or pfSense and pfSense or OpenSense. Have you seen many exploits and attacks on those kinds of firmware?
So personally, I have not, but I can't speak on the terms of everyone. Typically, my job actually includes a lot of embedded research. The fact that I got this sample on my desk is actually kind of an artifact of the fact that it was an exotic architecture. So someone from our malware team probably could give you a lot better answer to that.
I have a question. This is Phil Neary from CyberX. When we first read about VPNFilter, we thought it was strange. What are they doing looking at Modbus? Why are they going after SOHO routers? Would a potential theory be that SOHO routers are commonly used just because people go out and buy them even for their plants, and that this was really a cyber espionage type of operation?
I think that is probably a reasonable assessment. Personally, I've been to some of these sites, especially smaller, kind of regional, power distribution or the like. They're not using super high-end equipment because they don't have the budget. So if they need to have their engineer be able to work from home, he might go buy something from Best Buy and set it up at home. And if he can get it working, then so be it. I think that is common, and I also think that the people that are authoring this kind of malware realize that. It's not always going after the largest effect. If you can get something built like this much cheaper than going after, very large utilities, then you still gain viable intelligence. And in addition to that, you might be able to go after a smaller co-op and then somehow be able to pivot into a network where you have access and you didn't actually need to go after, finding a new 0-day in a high-end product.
Great. And did you say anything about the geographical distribution of where this was found?
So it was widespread. There were definitely some focuses, but I did not disclose that.
It was in the blog post. I know you don't want to talk about
Okay.
attribution, but I do believe a lot of it was in the Ukraine. Am I wrong about that?
No, that is accurate.
Okay, thanks. Any other questions? Great. Thank you very much, Carl.
Thank you.